it's interesting that each of you has very somewhat diverse interests in today's communication protocols, testing, and I think I can promise you all that my comments about the OFW are far from facetious. I'm really quite serious about it, and Sniffer is in fact very useful in all those concepts. It wasn't per se designed for all, it really was designed for support type activity and helping with problem solving. And Network General is a company, small company, just over a year old when I started. Some other people out in California. And what we do is to design service equipment for local area networks. And that equipment generally is designed to provide the same kind of capabilities that have been developed before the wide area networks. Generally speaking, the kind of things they use in, say, SMA networks or then BISYNC networks, trying to deal with the same kind of issues that those networks had in many ways. Addressability issues, performance issues, various kinds of connectivity issues. Of course, what makes it slightly different is that local area networks, often the problem that's being solved is not just a communication-related problem. That is, we're not just looking at, say, terminal emulation, some kind of communication-type application, but in fact you have a real distributed computer system. So then you get involved in issues having to do with loading, load balancing, use of servers, and file I/O, and things that perhaps didn't exist in the general communications world. So it's a more complicated problem, but it's the same kind of problem. The same kind of questions that you deal with have to do with system configurations and balancing channels or menus or whatever the analogy would have been in the wide area communication world. The same kind of problems exist in local area network world. So while the products are very similar, they do differ, of course. And the main differences have to do with small things like we're talking about 10 million bit per second communication lines and 19.2 bit per second communication lines. We're not talking about merely one protocol like an RDE protocol or 5-bit SNA, something really complicated. The protocols that are orders of magnitude more complicated than SNA. Multiples of them exist in the network. I was real clear yesterday they were not. People said, oh yeah, sure, PCI. I'm not so interested in. But by the way, we have XDS. By the way, we have COWS. By the way, we have TCP/IP. And they may be on the same LAN, and maybe, by the way, they might be one-bed products. So they just turn green back there. That's really what it is. So I think the challenge is we view it as very similar to the kinds of problems that exist in layer networks, but in a much more wild and woolly and uncontrolled fashion. And it's going to be interesting, in quotes, fun, in quotes. And anyone who's not ready for that, it's going to be a real surprise. So this is not the kind of real control, smooth down kind of environment that you might have in the world of cash registers, point of sale terminals, something like that. Most people don't buy software for the point of sale terminal down to the local computer shop. You mention cookies that they're going to do it on a PCI environment and expect it to both work. And expect somebody, whoever is multiple years, to fix it. Sorry, good morning. It's such a cheery note. I have good news. And I think the good news is, that Sniffer will make major enhancements to your ability in various areas to tackle those problems. It takes what were probably pretty grim and frustrating problems and boils them down to still serious but manageable ones. And that kind of leverage and that kind of extra ability that Sniffer brings that you'll get some feeling of today. Now, we emerged from my own experience in a former company that I began in 1978, which was in the business of developing, selling, supporting in the kind of small scale PC local area networks with dedicated but not PC-based servers, 68,000 bits, and going through a lot of the frustrations and agony that we sort of alluded to. Building those products, as you talked about, getting them out, getting through field tests, engineering development and vertical emulation, customer support issues, customer satisfaction issues. And what happened was, within within that company, we built some internal test tools. Those internal tools were used by primarily the engineering group and filtered their way out in a very unofficial way to the field support group. Had their group secret things that they solve hard problems with. And it became evident that this was really a very common technology. We spent about 5 years developing those tools, and the company was not in the business of selling tools. That wasn't their business. They were proprietary network and nothing to do with and so on. And so a year ago, I left with some other partners, and we purchased the rights to that technology, enhanced it, commercialized it, made it available for the kind of networks we're talking about today. So it's in many ways very rebuilt, very mature technology, although you're seeing it fairly early in its public disclosure. It's really very sophisticated in terms of having been used within the company that has to deal with hundreds of customers with thousands, tens of thousands of nodes on lamps, running multi-megabit speeds, and back doing the kind of things, flying doors here and there, and putting things together, and running multi-vendor software for two manufacturers in the same LAN, and trying to sort out what happened if one broadcast and brought down the other guy's server, and minor things like that. And software that they bought in computer shops, and based on some consultant's recommendation, and trying to sort out that as well as we do. Those products that we have, called Sniffer, are available for several different networks. First one, the Token Network, they developed Ethernet. In general, we're supporting Starlink, and as well, we recently announced that we are having an ArcNet version of our product. Let me just give you a quick view of some of how that product is organized, and we can talk about what's wrong with DG. Basically, we have versions of our product which can essentially collect data from the Ethernet system. And then, depending on what kind of software is running the Ethernet system, you may wish to interpret that data. For example, there's some software specifically for PCI environments. It knows about all various software protocols. We'll talk about what they are generally. It knows about the software you need to make sense out of PCI. And if you install or use a copy of that product, it sees anything else, it sort of recognizes it generically. It says, I don't know what that is. That's something. So it's someone else's work. It's there to capture the data and shows you the level of text. But it really doesn't understand how to format the packets and what the meaning of the message is going to is, something like that. Similarly, we have a product, a set of interpreters for TCP/IP, which is actually shorthand for many, many other protocols that are generally found in TCP/IP systems. On an EVM-based system, university. And again, one of our customers could order a version of the product for Ethernet with TCP/IP software. You may also specify that you'd like to have a Ethernet version product with both of these decoders, both of these interpreters installed in that same unit. When it comes to specific configurations and how this will actually work inside of DG and how the orders, I don't know what the mechanics of that could be, but technically the product, you can have a version which knows TCP/IP, which knows TCP/IP, one which has both installed, and then something that others will say others. There are additional levels of software available, for example, for Sun Microsystems type applications, which will be present on equipment manufactured by Sun as well as a number of other manufacturers that use those same protocols. Many of the Unix, VAX Unix type requirements use these protocols in the TCP/IP context, as NFS and LATEX. Then, for instance, there's another package which is available, and I'll refer to it by manufacturer name. You can also talk about what the pieces are, but for example, Novell has a PC-based environment for PC networking called Netware. It's based on Xerox XNS systems, their own file sharing system. There's a decoder for that. There's another one that basically supports environments that are running software, PC-oriented software for companies like 3Com and other VAS. They have a similar flavor software. And again, you can mix and match what stuff. So these are very soft. There is no reason why, for example, there could not be a protocol interpreter or family of protocol interpreters that would handle XTS, X25 protocol, Zodiac, okay, or CEO type protocols, or terminal emulation protocols that is shown as working on. Okay, how exactly they're packaged? I mean, there's another issue. Formally, any combination of implementation needs can be considered a problem. We can talk about doing that. There's plenty of room to expand these protocols. That's something that Network General is doing. For instance, one of the options that's not on this list is DECnet software. DEC runs their own protocols over Ethernet. Okay, and that's a candidate for this list. XDS. One thing that I'll point out to you, and we have some documentation which we'll hand out in a while, the manual and support for the system. The standard product that we sell, the one that you will have available internally, permits end users, in the sense that is people outside of network general development, to add decoders for these other options. Okay. So XTS is a good example. XTS coexists with PCI software, and it is basically interpreting packets that are off of a different service access point than PCI software. And one could write a routine to handle the formatting and display those packets in whatever format someone felt was useful and beneficial. Link it into the system and then generate the system PCI and XTS for terminal emulation for CEO messages. And that can be made available within the user standard. As the standard one is distributed, everyone is desired. And basically, when someone gets this, you provide sort of object libraries for various interpreters, and you can add a key to that and recreate a customized version of the system. Okay, so that's sort of the concept. And then we have things like, for example, a different hardware collection engine for Starlink. And probably there isn't anyone running, some microsystem software in Starlink today, but if they did, this could support it to varying degrees. So generally, the hardware engines and the software decoders are fairly orthogonal and can be combined together in different fashions. So, for instance, we mentioned that we had a token ring. This is the 4 megabit IBM token ring version. And in that case, there are instances where there is no software running on that. Haven't seen PCI, so these companies are available there. There's some other software that really is only supported by IBM on the token ring, such as their implementation of SNA, U6.2, EPC, other things that other manufacturers have to be something compatible with, so they probably will. We know some companies that are running TCP/IP, for example, over token ring, and so on. So this matrix, we can fill out depending on what the manufacturer chooses to do. ARPANET is a non-standard UPF2 sense of the bus. And there again, there's one particular manufacturer's proprietary software data point. Work on that. DECnet. And we envision that this list will continue just like that. So things like MAT, the broadband, bus. Right. Or maybe some manufacturers proprietary network of some kind. So one of the things that people have asked about, certainly another possible network technology is some kind of SDLC or HDLC. serial type link. You might look at x25, packet switching x25 sets. Which fit in the same compartment. Generally, not addressing traditions. There are companies which do that. Something we look at, or look at their problems. In terms of the actual units, the forms that is planned to be available within DG are a desktop unit based around the developer -286. In general, most of these boards require high performance implementation that reviews 16-bit ET type of bus, very high performance VMAs, things like that. The exception probably is Starland. In fact, in that case, in the case of Starland, the implementation that will run on the DG1 Model 2 is battery powered and be used in real lightweight field type applications when that's needed. There's nothing, for example, Network General actually sells its packaged products, and we use a compact portable too, which is a 286 16-bit bus machine. There may be reasons why maybe DG in the future would have some kind of portable type instrument like that. Obviously, be packaged like that in certain cases. I think that probably some units like that I would recommend as being worthwhile having. When you have to ship, it's just more convenient to ship that to a customer in a remote place to set up and shipping them no bill. Purely convenience issue.
Yes. How is the Ethernet star
Absolutely. Certainly, in general, the limitations on how many of these are in a given machine really relates to physical limits and how many cards you can put in, and do you have the right slots of power and things like that. Generally, these are separate programs. From the user's point of view, you start up in the Ethernet version, or you start up the Starlink version. Once you're in the program, you would have all or some set of these software options built. There may be reasons why someone would choose, and customers might configure it that way. We've seen it, where they would have actually different copies of the Ethernet version on a given machine, one of which had just some of these protocols, and the other ones had others. And that has to do more with some buffer space issues, which we might talk about later. Well, I think the actual distribution software for a copy, including the libraries and files and building them on, is between 1 and 2 months. It includes various sample files and DOS and everything. We generally use 20 megabyte hard disk with the system, and so all disk files built built space. So 40 megs on there, eventually people will accumulate 40 megs worth of traces that they collected. It's never been proven.
just thinking more build having instructions in my build.
Well, I'd say that generally it's like bags. So anything more that's on the hard disk is available. In terms of performance, there's very little reason to especially have high performance disks. If you want to have a very low performance disk, it's for loading it, but once it's loaded, it's basically memory resident. Except for saving, loading stuff to the disk, you actually capture a file. There's one case with the lookup where you actually will be using a file as a lookup table for names, matching names and addresses that you might see on the network. There, the speed of the disk is relevant, but in general, that would not be a issue.
Yeah. boards that actually support the physical network? Are they're all customized? They require special boards?
The answer in general is yes. And the customization of the board will depend somewhat on the technology. And our style has been to start with boards available from OEMs, such as Fastboard, such as Board, and select particular ones based on their features and performance. For instance, for Ethernet, we actually selected the 3COM 16-bit board with microprocessor board and so on. Customization in that case is to replace totally the software on the board itself that directly interfaces with the microprocessor on board, so basically the first level packet handling and time slicing and filtering and various things in dedicated fashion, as well as increase the memory buffer size. But other than that, it's a minimal board that is put into a rather standard. In the case of token ring, a similar thing is done that we use a fairly standard implementation in the sense of using a Texas Instrument chipset, microprocessors, and so on. It has custom microcode to be able to capture traffic. Generally, the Ethernet chips support the ability to capture all packets. Token ring chips absolutely don't do that. ARPANET chips absolutely don't do that. And we have to do some pretty things you don't talk about. Big companies make that happen, make that work on token ring and ARPANET, because they're actually at a very low level in the chipsets. They don't want you to be able to do the packets that are not destined for your station. Starlink Ethernet. That's a standard feature of the chipsets. Yes. Yeah, those will be unmodified common board. So in that case, because of performance, they're just going to be very low level buffer on the boards and moving the data right as opposed to going to talk to those hosts Starlink one megabit. That's right. That's correct. Generally, as far as we can tell, a threshold in terms of some worst case back-to-back packets and usual latency interrupts. 1 meg is comfortable, 10 meg is impossible. You must do that on the intelligent adapter. 2 megs is about the threshold. So when you look at some other 2 meg systems, IBM has a 2 meg network, and wind's blowing your direction. And which probably means you can do it. You can't do it. You can't do it. You can't do it. And certainly gives you margins that are announcing. But 1 meg is not a problem. Assuming that it's doing that you have a chipset at the level of the integral national chipset that do this. Talking about other networks, which are slower networks, these kind of networks, running at hundreds of kilobits per second, and some of those typical communications controllers give you a character level interaction that's not visible. Worst case, while we're on the subject of configurations, so I have talked about a little bit about the packaging that might be available, software. Essentially, the emphasis is on PCI. Okay. But surely all the agreements and arrangements are such that other options are available, and how specifically anyone here or someone here would get a version which has PCI or something. The company will work out these options, but any combination is available. Makes sense. The last thing I will mention in that line is another feature which is quite relevant as the configuration and the support that we've not yet released and is still in test phase. That is remote access, the ability to run the equipment remotely. It's a very important feature, essentially supported by the use of an internal modem, or in our case, external modems in the serial port. The external environment uses at least 2400 baud, an ASIC environment, and generally what it provides is the ability to send a unit to a new location, have someone install the unit, and then dial into that unit and fully remotely, in quite interactive fashion, be able to start the unit, stop the unit, move the display, scroll around if necessary, do some analysis remotely, cause it to then send subsystem frames off the phone line. You might have another expert, a developer, or someone that really needs to look at it in more detail, and you can then send that information off the phone line, print it out, put it on a hard disk, whatever strategy, and that will be available probably as soon as the product.
Do that, you must have to see the itself.
That's right. Now, but the load station needs to be nothing more than a PC. A PC, yeah, but to handle the function of the screen. Logically, it's no more than a terminal, right? It needs to actually be some kind of workstation because it will have capabilities to upload stuff and so on. Then to do the actual analysis, if that's what you choose to do, you can then take that to scan. So those people that support that do nothing more than say, did you want to dash it? Then they can take that to scan or something else, whatever, flag it to scan, and send it to someone else who has to stick their dash and do analysis, developer center. And it will have some really nice things like the chat mode. So the idea is you can have someone in the field that you can ask them, well, please go off, go over and type this and also load this MD and change this parameter, do them some instructions and see what happens, and basically use them as remote hands and eyes, but do really all the technical analysis. It works quite well. Another opportunity for people who are more in the TCP/IP type environment, certainly that I'm familiar with, and it may apply to some of the Zodiac type environments too, is to accomplish exactly what we described, but where the output, the serial output, then goes into some kind of terminal interface unit, NIU, I don't know what, comes there. Where in fact then you are dialing in not through a direct dial type system, asynchronously with modems, but going in through a packet switch network, in which case you could conceivably go even at some higher speeds, and basically then just loop it back from the network, assuming that it's functional and not low densities, just loop the output from the super serial port into the region, pull it on some terminal concentrator unit, and then have some other access patterns that we have good transparency. The exact schedules are still being finalized. There are a number of units that are already here at EG for evaluation, test, use, and so on. There are several, I think it's 2 or 3 units packaged in actual compacts, which can be sent around 1 or 2 units. And as well, there are another 4 that are in Velcro. I think 3 of them are downstairs. Exactly what we get some hands on. Let's go through a little bit the general capabilities of the sniffer and what it's doing. I think the simplest way to understand what it is primarily to just think of it as a device which is doing wiretapping on whatever wire is connected to it. Just think of that rule. It can't do more or less than see what's going on that network. That's the bottom line. So if there's traffic on this network, it's going to reliably tell you that. There's no traffic on the network, it won't tell you that. You have a gateway here, and some other network here. Again, the rule is it always sees the packets here that happen to be going by here. Alright? And if there's traffic on this network between one station and another, if that information is not present on this side, it doesn't see it because it isn't there electrically. So we're working on a new model which will incorporate GSP and You can't do that. So you have to send a sniffer to the place where the problem is, or perceived to be. You have to physically connect to the network. Obviously, if you have a complex network, but there is some kind of fault, then the fact that you only see certain subset of stations of traffic is at least an indication that, gee, you're not really connected to that other building, you're really not connected to that hub that you thought you were. And you may then want to connect it to some other location. One thing that we are more seriously looking at is a version of a sniffer which could potentially collect data from two segments of LAN. These might be different technologies to specifically look at problems that are relevant to gateways. Nonetheless, it's extremely valuable, and we'll get some idea of specifically how when you're looking at gateway problems in any case. On that subject, an interesting kind of configuration that's quite useful is where your network has been configured with some kind of main bus type philosophy with some networks that somehow being switched through a common core bus or a common core nucleus, like the same technologies like the Ethernet, these might be small lambs, Ethernets with Ethernets connected. And putting a device here is very useful because then in fact you can see all traffic that's going from nodes. As long as there are two different networks, you can see quite a bit of what's going on the network. You wouldn't see traffic that's going right across it. In general, then, the sniffer is primarily listening to what's going on, primarily collecting data, it's filtering that data, they look at all the data, some subset of the data, and basically listening to us. There are two other capabilities it has, which are useful, but they're certainly not the design strength of the product. It's not our intention for people who are more in the hardware development, the vertical development, that they need much heavier duty tools in this area. We don't provide them. That's in the area of physical cable testing, the analog sense, and low-level protocol simulations and debugging and traffic interaction. In both those areas we have capabilities, but they're meant to be addressed in particular kind of problems. For instance, the first one is cable testing. Putting in a local area network system is trivial. I read it in Newsweek magazine. AT&T tells me all I got to do if I can install it on the phone, I can now install a network, just plug it in, and it works. Right? So why are we here today? We all would like to believe it's that way. It's certainly getting better. It's certainly getting simpler. But there still are, 1,000 ways to get it right and 10,000 ways to get it wrong. So that's probably going to happen. And on the whole, while lots of things work well, there are many cases where, for instance, you can have a marginal electrical connection, a bad contact, whatever you call it, on a modular plug that would make the signal quality across that plug just not optimal. And the signal levels might cross, they just want to have, their full oomph, and instead of putting whatever voltage they're currently should do is rated by 20% or 30%. And you have some margins of tolerance on the boards, and some of them will receive things just fine, and that's okay. In some other cases, you're going to have boards that won't really hear those signals very well. You don't have to worry, because we have these fantastically powerful local area networks, all kinds of checksums and retry mechanisms that will guarantee to notice. So it gets distorted, one gets changed to 0, they'll reject the packet, the system will retry, and it'll work. Now, it may work 5 times slower than it's supposed to work, but it will work. And that's one of the frustrating lessons about these local area network systems, is they're so incredibly robust that you can beat them and mistreat them and plug things in upside down and install software backwards and totally mistune the system, and they still work. And sometimes people don't even know that they're not supposed to work that way. They just, they've always worked that way, and they assume that's just the way these products work. they're in fact working very poorly, very far from the spec. That kind of low-level detail analog electronics to actually check signal voltages, 1.3 volts instead of 1.5 volts is not what it's going to for. Check that when you put together a cable, for example, with Ethernet, the Ethernet book is very careful to talk about the quality of the cable used, the kinds of connectors, and it's really very, very rigorous. No one in the world does that book unless they're really incredibly conservative. I mean, basically, people just hook it together, and it works. So it works. And they get connectors from Radio Shack, and they put terminators on here. I mean, all terminators look alike. And the fact that they're supposed to be 50 ohm, they have to be 93 ohm. It's a terminator, right? The system works, right? And things like that can go literally unnoticed for a long period of time. You're in there. And when you have a piece of cable and you have lots of connectors in the middle, there are devices which are referred to as TDR, time domain reflectometers, which is a very, it's 25-cent, $5 name for a radar. Okay? Basically, it shoots a pulse down the cable and looks for echoes. And for instance, if I have a perfectly terminated system with direct transmission line, that pulse will go down the cable and get absorbed, and I won't get any reflections. Okay? Or if I were to look with the scope, over here in this cable, I should see a nice clean pulse. If in fact it's gone through these kind of connectors, often what you see are some kind of fairly raggedy pulse. Worse and worse, depending on the quality of this, similar reflection. When you're installing a system at various points in its lifetime, you really want to get in there and do these kind of very low-level analog tests to make sure that these are starting off clean and so on. The Sniffer has a TDR. The purpose of that TDR is to look for gross faults. Okay, someone opens up a cable here, accidentally, inadvertently, takes it off, sticks it in the back of their PC, we still have that. Oh, a cable. I know where it goes. And there's some Ethernet cable in the back of their machine. And meanwhile, everyone else in the building is running around and nothing's working, and he doesn't understand why his work machine is not working either, so he thinks tomorrow will call someone to fix it. That's the whole system. Thousands of things. Never happened. Not around here. Mark has to very smart. So, the idea is you hook Sniffer on when that happens. And basically, what it will do is send down one of these pulses. And what happens is, like I said, in a normal case, the pulse ought to be absorbed by the terminators at both ends. Here, what happens is the pulse hits this conductivity in the cable, and it comes, reflection comes back. Enough reflection or down reflection, depending on whether or not there's a break in the cable or someone has shorted the cable together. In those two extreme cases, you get two different kinds of signals coming back here. There's a very simple calculation. How long did it take for that echo to come back? And that calculation, how long it took, by the way, is pretty approximate. By that I mean that, again, if you look at what that pulse was coming back, it doesn't look like this. It's not a pretty pulse. It's something that you've got to figure out, well, where to where. Was it here or here when the echo came back? So it gives you an idea. It knows how long that was, roughly within, nanoseconds. Speaking of it, tells the nearest mile is right. It is building. But it tells you within 20 feet where it is. Assuming some other things. It basically calculates that time, translates it into distance based on how fast signals go in various cables. And there again, in the Ethernet cable, speed of the pulse is one rate, the Ethernet cable is some other rate, there'll be a fiber optic segment in the middle or a gateway bridge. The numbers are approximate, and at least you know roughly where it is in one of two directions. So you say, you say, okay, I'll go this way, you go that way, we'll meet around there. And you watch down the corridors, and of course, everyone knows where all the cable goes, right? No problem. They carefully maintain maps. They know exactly where the cable. That's right. Everyone knows that there isn't, no, there's not 500 feet of cable. Never happens. Never happens. But it's meant to solve, in fact, what I think is the most common failure is, a total failure. Someone does something totally dumb, runs a drill through the cable, steps and puts a chair on the cable, shorts it. The ones that are frustrating is when he doesn't quite short the cable. He merely pitches it badly. And, that's a case where, in fact, the network will simply perform very, very slowly. TDR will tell you much more fluidly where that sharp is. There's no card or ruling. You vaguely know that it appears as if there's an unreliable short somewhere 200 feet away. So that's one case in which the system does transmit. And the other case that it transmits is a traffic generator. And this traffic generator capability, again, is meant to resolve only some very simple questions. And those questions are things like, gee whiz, is the reason the network really slow because the network is so busy, the cable is so busy, something like that. And it's meant to convince you to simply generate totally useless packets to a specific station or to a station's address, let's say it doesn't even exist. Just make up a station address that's not on the network, and this thing will inject packets of a certain size at a certain rate into the network just to give it some kind of background load. Okay? Yeah, I think with a single sniffer up to something like 30% of the network load, which is far more than a network ought to be operating at, and then see whether or not a particular application, in fact, is very slow. And I think it's almost a marketing tool. In many cases, that you will say, well, it's not that the network is slow. Here, crank up the network 30% background, and it still doesn't run any slower, doesn't run any faster. That wasn't the problem. And always considering that as a real issue. There are cases where you may want to use it. You actually can specify what the contents of part of the packet is. And there are cases when you can actually send packets to a particular device and send them with a protocol contender that they will receive the packet but otherwise have to ignore it. And just test whether or not that device is alive, is responding to packets, what happens if it gets 500 packets per second. Even though they're not really connected. The reason that that's important is because realistically in these networks you do have different services from different people, and it's quite the case that different vendors, when they start off or whatever, send out broadcasts, and your software is going to end up with essentially random packets that some other vendor or some PC software just sends out, and you have to be very defensive. And boards go down, certain manufacturing boards every now and then just decide to have fun and talk to their friends. Just send stuff out on the network. And those things are always going to be going on. And generally, a lot of software that you test in the lab here, my experience at various companies is it's tested against your own software. You're just not in a position to bring in everyone else's world software. And so have it running also on the same network is to make sure that you're or ignore each other. Right now, see that everything is powered up and takes out all the aisles on the hardware. Really? Well, we haven't had that PC. So it's good to do that. Now there are again other products, there are other technologies, particularly in the area of wider networks. To use this analogy, where people used to SMA emulation or Bison emulation, where you actually will simulate half of look like a host, look like a terminal for debugging complex problems. This is not at all intended for that kind of area. So those are two cases: you generate traffic or some kind of data on the network. On the whole, it's meant to be passive. So what we'll look at is now sort of the features that it has to collect data, and we will do a logic review of what happens in the sniffer itself. At this point, let me mention that, so we're not really going to talk anymore about the cable test or traffic generation, but instead the receiver packets. Sniffer is a super product for seeing what happens, okay, and it sees anything and everything. If you think about that model, think about the dual wiretap, you get some idea of the limits of its capabilities. Some people are really surprised when they start seeing passwords and your electronic mail and whatever messages to friends and company. It is very common to put a sniffer iPad on systems and see people play games. Very often, you just turn it on, press one key, and it will show you terminal traffic, and you can see, 3 hits with a magic wand. You want 22, gold, 22. That's right. That's certainly not eternally. If customers want to do this machine, that's fine. Obviously, Sniffer certainly could be used to some pretty nasty purposes and very efficiently and very effectively. You want to see what the abilities are. In fact, you can run the random stuff around. You can really hone in on something and find an activation of the tool. And I think that it certainly, as you'll see, it doesn't go out of its way to do those things, but really have no concept of just how vulnerable the data communication data is in network environments. It's just simple when you stop to think about it, but you're in a large network, you're in a huge office building, you have valuable company data, and traveling in one cable that passes by everyone's office in the clear. It didn't take a sniffer for someone who was interested to figure out what it is. They could just take a DC, go to the computer lab, get a 3-pump board, and hack together a program in an afternoon. They would sit there and find every packet that said password equals and copy them. That's an afternoon's job for hacking. So I don't think that we're making that any easier. Certainly not for the people that you're worried about. Unless you're the guy. But it is really, shocking just how easy it makes it. The other side of the coin is the reason that it makes most things easy is to help a real problem. When someone says, I tried to log on to the system, I typed my password, and it said access denied. Fix the system. Whether it's saying, no, you didn't type, 1, 2, 3, you typed 1, 3, 2. Person try again and say, well, this time it worked, but or it didn't work, fix it. Yes, with software for that particular model. So you can run that's right. It's a superset. It keeps the basic functionality. It's such a way to do what we call the plus 3C505 work. So if you have TCP project. No. But I think they have something. As I said, the rule is you need to drive over that board. Informal. In general, that's not the goal. And if it has to work, good, it doesn't work. We're not promising to do it. We have to do it 3-pump boards now that the US boards are available. I'd say in the case of Starland, definitely, it's the same board, for sure. I think for most of the PC-oriented type stuff, it's less than likely to be useful. For people who are in the TCP/IP world, in fact, it's more than likely to be useful. That those boards tend to be available, and what you're trying to do is something like Telnet or FTP. That's a reasonable thing to do if the works. PCI is probably not likely. On the other hand, there's no reason why principle that another slot, the same machine, you couldn't have in fact a PCI board connected to that same Ethernet, and send stuff to and from it. There may be some minor technical issues. In fact, we haven't specifically addressed that where they might have to use the same interrupt channel, interrupts or something, but there are ways to reconfigure around that. So I'd say that's reasonable to expect to at least do that. We're talking about the security thing, and on one hand, certainly from the customer's point of view, there is an education process that's necessary to really get the job. They see that person receive spoke, you can ask, we got the protocol, CEO WS stuff. It translates it, there it is. It's very important for you to do base, it's very fast, responsive, consistent information, it's not very fast. You know, search for things, certainly makes your life easy if you're spooked. I would say, though, that the other side of the coin is really important to stress. And that is that probably people who are worried about those things often take a really defensive position against hackers and other people who are really trying to get into their corporate data and their secure systems. So we all know that we have this server, let's say, and it's got excellent password security. We believe it works. It's not fixing right. That's not the issue. The question is, what do you do with someone in a PCI environment who writes a program in BASIC that just tries every password, If lots of articles written that say, use the 10,000 most popular words in the world, and chances are, 99% in 1 hour you found the password. And use essentially cookbooks that tell you, how to go about finding someone's password without being very bright. So I think that what you want to look at is using something like a sniffer, as you'll see, to record traffic like logon rejection. And something like that, access denied failures of files. And when you see, 500 per hour coming from a certain destination address, it might be time to go have a little chat with someone before it breaks the system. You never will. Okay, your password security and so on is such that, really don't represent, that's a challenge that you still think the system is up to. But that kind of behavior is against policy. So, on balance, I think that it's going to help enhance that stuff, but it's a hell of a shot to do. They just didn't realize that that's what they were getting into it as well as that. Big business about a subsidiary of cryptography company. No bill sticker, that's true. Basic flow of data is from the network onto the adaptive board. On the adaptive board, packets are looked at, and a quick decision is made to accept the packet or reject it. For example, generally you may accept all packets. You might decide you only want to look at traffic from station A to station B. Any packet that doesn't have the right source and destination address doesn't get collected, the others will get collected. And you may want to look at certain protocols. You may specify a hex value. Like the log on rejects, we don't have a verb sniffer that says log on rejected messages. But you can figure out that basically, certain packets that happen to have value 27 and this byte and something else, that's at least a superset of all packets. Just those packets, but include most of those packets, high percentage of packets. So you can set up those like that, look at those things. And this board itself, to explain, has hardware buffers, which are finite hardware buffers. In other words, it can only handle so much data before its input stream gets back up. So if you do that in the case of Ethernet, actually for 500 kilobytes of data basically initially. For example, take worst case traffic, 100% of the bandwidth, until it's full. However, once that gets full, which if you're in a lab type situation or your network is absolutely bizarre, could be a second or two. And at that point, you can no longer accept the packets, process the new ones, close them, and so on. And it may start to lose packets, and it tells you that reliably. There are ways around that. You can specify that you only want to keep a portion of the packet. One good way is to increase the throughput. reliably without really losing any information also deals with a security issue. To say that you only want to keep the first 128 bytes, 256 bytes of the packet, how will the rest? The system remembers how big the packet was, remembers that there used to be 732 bytes in this packet, but the only data it keeps is the initial portion, which is generally enough to diagnose any problems that we were talking about here, about software and the file I/O and so on. So we're collecting this data, and while the data is being captured, there are some displays which show on a screen, as we'll look at in a minute, what's happening, who's on the network, how the connections are going, who it's to, who it's from, instantaneous rates, instantaneous throughputs, give you a real feeling for the nature of the data that's being collected. And if you look at this drawing here, schematically, you can see that those displays are operating after the filter itself. So you set up the filter, which is just look at traffic to and from a particular server, any station or server, and these displays will show you the traffic only to and from that server, and how that traffic is distributed, and whether that is 5% of the network bandwidth or 5%, and so on. Similarly, if you set up these filters to, for instance, collect only misform packets. For example, if this form packet is a packet that is too short to be a legitimate Ethernet packet, and generally produced by collision network, you can collect just collisions and see in real time the collision rate, what bad packet rate or other kinds of bad packets will see, and that might be a useful clue. An example of a problem like that is quite typical in Ethernet systems. In Ethernet, there is a limit on how long you can make an Ethernet. It turns out that the reason for that limit doesn't really have to do with how much cable you can drive and so on, so much as in order to deal with the collision problem, one wants to ensure that if this station sends out a packet, because he decides that there's no one using Ethernet, and this station decides to start sending a packet because no one's using Ethernet, that in fact, when these two packets at the speed of electrical propagation sort of run into each other and start to interfere electrically on the cable, that both of these stations will in fact recognize that phenomenon before they completely transmit the packet. Which means that the packets can't be real tiny, because if they're real tiny, they just go on the cable and it's gone, and the problems that happen sort of later somewhere else on the cable, you'll never know about it, you'll never retransmit it or adjust your algorithms, which have to do with that busy network. So it's critical that all packets are a certain length. And what can happen is that users simply decide that, gee whiz, they add another station, that's fine, let's add another piece of cable. They add another piece of cable, they add another piece of cable. And in general, you can do that for largely on the Internet spectrum, and everything works. Everything seems to work. And there's pathological cases in certain stations, sort of VPNs, that tend to have more errors and problems and stuff like that. That's where the server happens to be in your case. It might have very severe effects on throughput, although things still are functional. That's a fuzzy little problem. And you can detect this, for instance, by noticing that the collision rate here was in fact much higher than normal. And by looking at the so-called collision fragment, that is the first portion of the packets, before they get caught, you can see, you can actually figure out who those packets were coming from. And by reason of looking at that, say, aha, that those are not random packets, the normal collisions would be equally distributed. These all seem to be coming from the station called Steve. Weird, another station called narrative. And called the language ones, and say, aha, those are, and various other possibilities. Or something, but it might very well be this very simple problem. That's a typical thing that will happen, won't happen in the first month of the system there, but 12 months later. But after you look at collisions, and and other kinds of bad packets. At the same time, the packets that are being collected that meet whatever this criterion are going into a buffer, which is actually now in the workstation itself, in the Velcro, in the DG1. And that buffer is 256 kilobytes big here. And in the normal way that you would use Sniffer, you just turn it on and don't change its defaults. If you have more than enough packets, they just come in here and out the other end is a big bucket, and the system keeps running until you they just keep traveling along into the big bucket. If you don't otherwise do anything, so you can collect that, you press the stop key and see what happens. But in these cases, you're probably just paying attention to the meters and counting. What disregard from the start is first name, to wrap around. You don't have to. There are options you can look at later where you can say, listen, stop when the bar fills up. So it'll fill up and stop, maybe go deep or something, stops capturing, and you can see what happens. So for instance, that's not a reasonable thing to do. You might have some problem, okay, that you're looking at, you set up some filter that will capture some particular events. You start this application going on PC, and you don't know whether or not the problem's going to happen in 5 minutes or 10 minutes, and exactly what it's going to be, but you just want to see what's happening after this. Meanwhile, you can go have a cup of coffee because you don't know how long it's going to take. You might very well set up the condition, tell it to stop. If it's full, then you're going to come back later and either see that it happened, press the stop key manually, or you at least have seen everything that happened as much as it could for the time that you set up this test and left. Another way to stop data capture is with a trigger. So there is in fact a trigger event that you can look at this data stream for a packet that has some particular pattern in it. Like you might want to look at the sequence of all record locks. PCI records. And when that trigger occurs, you can do various things with it. You can stop the capture instantaneously. Meaning when the trigger occurs, the event that caused the trigger would be here in the buffer, and you would see stuff earlier. You see as much as 256K, the trigger being at the end of the buffer. Alternatively, you can say that you want to start collecting data when the trigger happens. That is, you like the trigger eventually to be here in the buffer, and you want to see everything happen after that trigger occurs. The system will stop, or you can center it. Yeah.
These packets of times,
yes.
Are they too complicated?
Actually, these are clock that's up here. And the internal accuracy, I believe, is something like 10 microseconds. Which is available through one of the windows. The displays that you actually look at are typically much grosser than that. The actual displays on the screen shows it like a millisecond resolution. There's a kind of events, the kind of numbers you want to look at are often seconds and tenths of seconds. Internally, it's very accurate timestamp that's kept, that's in the files. There are ways to access that. The packets are also stamped with the actual absolute time of the day and day of the week. That is initialized using the time of day, clock in the PC that's running it. So if you have visualized that, you may find everything, for 1980 or whatever the beginning of the universe was. But then relative to that. And it will reliably keep track of events that are happening in the days. It will move around those clocks very high. And there may be cases where what you're looking at is such a rare thing that, in fact, conceivably, one extreme is to put a unit on, put it on trigger, and leave it for a week until this event randomly happens again. At that point, hopefully, have exactly the information necessary to find out how the hell it happened and fix it. And we'd like to see that it happened 3 days into the testing.
Just from those details, on the board itself, it's on the big board.
The timestamping of the packets is done, yes, by our software on the pre-com board as they are accepted.
Using the pre-com boards.
Using a counter, using a microsecond or 10 microsecond counter that is running on that. And then the base of that, the T0, when you start collecting, is actually, absolute time of day is got from the PC, and then that's added to it as an offset. Let me say a little word about this, the capture buffer and capture buffer size. The product today is running in a DOS environment, an EC DOS environment, which basically gives you some restrictions that you have 640 kilobytes that DOS is managing, of which part of that is taken up by DOS itself, whatever. And then the program and data space falls in here. Generally what the sniffer will do is the code is loaded, it's all resonant, which is why the speed of the host PC is speed of the disk is not very important. And then it allocates a buffer here, which is actually no more than 256K. In general, for any one of those protocol interpreters and any two of the protocol interpreters, those combinations of the protocol interpreters, there'll be room for 256K. But if this has, 5 protocol interpreters installed, it gets bigger. And in fact, this space may no longer be 256K, it may be only 200K or something. Well, that's a reason, not to necessarily have, even if you're interested in the situation where you want to occasionally look at TCP/IP and PCI and Ethernet and so on, you might want to have different versions of the sniffer installed on the same machine, so that if you're always doing PCI, you have the full size buffer. Yeah.
Are there any plans in the near future to at least take advantage of extended memory for the buffer?
Right. Then next change in product would be to have the full 640K used for sniffer and protocol interpreters. There's table space, other tables that have to be allocated and so on. And then all the buffers will live above 1 megabyte, which is why 286 is important or some other type scheme. And then realistically, this is limited more by hardware than software. Here you're going to see things like in the 1 to 2 maybe 1 to 2 megabyte would be typical buffer sizes. Yeah. And that will be available now the first release of the sniffer to the DG, but that will be an upgrade later.
It's pretty slow, right?
I think that in the case of 16-bit boards, it's not a problem because they can be made directly into that. So, as data is being collected, it will actually very efficiently go into the memory from the hard network adapter. And then through the MA. This actually works out pretty well. And then when you're looking at it on the screen, you'll be transferring it, but you will notice delays, millisecond delays for it somehow. Address that and swap it down. So it seems much reasonable, maybe so. We haven't done it yet, so.
The trigger and connectors, those are all in the board.
It's included there. Below that is actually on the host. So that one portion of it, part of the capture filter is not getting triggering. I guess right now it's not done on the host. It's not done on the filtering yet. That's an area as we see triggering and filtering from the point of view of text data. It's kept very, very limited. And it's a very, very simple term that you can use to capture it. that's another area we'll talk about. Extensions that I guess we certainly need to add some additional options there for and exploring, although certainly our plan is very restricted. With these discussions, for example, some people say that's great, you can look at traffic between, all stations, for instance, look at stations between any wildcard and a server, between station A and station B. I don't know if it's traffic between A and B and C and B. That's really important. Yeah, right. So, there may be some stations in that area. Okay. Once the data is collected, it's in an in-memory buffer. Okay, it's not just moving to disk or streaming to into memory. That's another area that's much more controversial, is whether or not, if the data rates are low enough, this data, in fact, could or should go directly to the disk. Okay, certainly there are some people who, if I were in this manufacturing business, it sounds like a great idea, because I would surely ship my snippers to a 100 megabyte, 200 megabyte disk. You just turn on and do it. Very quickly, fill it up, even at low data rates. Even at 1% busy Ethernet, 1% busy Ethernet is 100 kilobytes per second. Just let that thing run for half an hour and on to find a disk. So that's called IBM option. But right now, until we get to this business, we keep the data right in an in-core cache buffer, which also is very fast and snappy for now to certain price until scroll things up this rather than later. And you can then analyze the data and look it on your screen in various ways. And again, do some additional levels of filtering. And this filtering is at least as powerful as this filtering, and more so. For instance, here you might be collecting all traffic for some reason. Having collected it, you might say, aha, I really think the problem is between station A and station B, so you can now turn on the display filter and say, now I want to only look at station A and B. And for all intents and purposes, the system is fast enough that it just instantly does the filtering on the screen. You only see that portion of data you want. You can page up, page edit. It looks as if you did that. If you're looking at some really rare events that are separated by thousands and thousands of frames, in fact, it does have to do a lot more work to filter out the data you want to as you're watching on the screen. It will do it, but it's not quite as efficient. There are some additional options that are available here, having to do with higher level protocols that are not available for runtime. See? And in general, then, you can take this data, when you're looking at, you can save the raw data to the disk, you can save the entire caching buffer to the disk, or you can save just a filter portion. So having collected data, you might have 256 bytes of data here, and then decide, station A is not talking to station B, frame number 20 and frame number 50, and tell the system just save those frames to disk. And that's the scenario that I envision in terms of remote access. Somebody will come in over a phone line, collect some data, not everything perhaps, but still more than the details necessary to, let's say, give to the developer, then extract by having looked around those particular frames which show exactly the problem, save that to disk, and then ship it off the phone line rather than shipping 256K or 2 megs. It takes a while. Shipping off a kilobyte, which is just exactly the frames that show the failure or the problem, performance issue. That will take literally seconds to look at. At the same time, the data you look at, you can print, and you can print it to a real printer, whatever language you choose, or you can print it to disk and basically take essentially something akin to what you're seeing on the screen to your printer, so you could, let's say, send it to another vendor. Let's say you've decided that the real reason that the system is having problems is not that the server implementation is wrong, it's in fact doing the doc protocol perfectly correctly, but this other vendor's code is just incorrectly blocking the file or accessing the file. And the customer is very upset. You might then be prepared to have identified the problem and said that is, the resolution will depend upon that company coming out with a release. Print out a listing showing a particular failure or inefficiency, opening the file, reading the same records 1,000 times over. You see lots of those kind of things. And give it to the customer, send it to a third-party vendor, and you can actually get out and solve the problem instead of just pointing the finger back to someone else and saying, oh no, our product works. It's pretty simple to look at that kind of stuff, even for other companies that don't have sniffers, haven't been to training 101, look at it and say, oh yeah. You get all these money calls every now and then, it's really delightful. So companies, what the hell is this here? Someone says this printout serves these problems on our product now. What is this sniffer? Where did we get one? The reason you might want to save that for this memory is that you may wish to do some other kind of analysis with the data that the sniffer again doesn't do. For instance, you might want to know what fraction of the file open command during a certain hour came from either the 5% of the 10% of the family, 50% of the something like that. The information to do that is available, but it's not accumulated together in exactly the way. It's on the screen, it shows who did it, it shows the file open, but you want to sort of just aggregate it. You could take the output of the sniffer that you would see on your screen or send to a printer, put it to a disk file, then ask you to bring it into virtually any database program today, ask the import command, and generally almost use English. Focus exactly the question. Show me column 2, sorted by column 3, and it'll print it out, plot it on your paper plotter, and something like Yeah. Yes. That's the same. Right. What is your there? Yeah. Let me change the package. What? Just a warm friend of that panic. Right. Generally, using it, setting it up as you see is quite straightforward. We're talking here about some sort of portable computer. Doesn't need any special requirements. Plug it in. Under 10 volts. Overseas, change the switch and once there. Setting it up is as simple as plugging in the wall, plugging in the network. It doesn't take any special requirements. It's on the Starline hub, it's on the Ethernet, it gets connected to the Internet. We'll talk about what that takes. But there's certainly no special precaution, special issue that apply to this than any other product. In any case of the network, what you see, in the case of Starland, I think there really are a lot of choices. And if that hub is working, and if it's connected to the rest of the world, you should see something. Part of the problem is that when you're working in an unknown environment, you don't know that the thing you're plugging into necessarily works. And one of the great mysteries in watching field service people is that even when customers or other people try to be helpful, they can be highly misleading. So you, oh yes, this one works, I guarantee it. And you can spend a whole day believing that, only to find out that exactly that is true, and that people before that people club has some problems, and that somehow relates to what you're trying to solve. Well, always problems in debugging. There's no more or less true here, but as an attitude problem, it's really important not to trust essentially anything. Ever. Even your mother. Cash, maybe. Okay, so plug it in the wall. That's right. And when it comes to connecting to Ethernet, Ethernet is a great standard. And like all great standards, it comes in all different sizes, flavors, and shapes. Standards are fine. So basically, there were, I was saying there were only two, and I was talking, we were chatting during the coffee break about some other standards. There are, we used to think, and there are only two possible sort of Ethernet standards that you have to worry about, which are basically the thick Ethernet and the thin Ethernet, or referred to as cheaper net. Which is a thin coaxial cable with BNC style connectors, snap-on type connectors. Thick Ethernet, actually there are several types of connectors that people use to connect to this. They range from these are called N connectors, which are big thick barrel type connectors that screw on, to vampire tap, which is a box that pierces the cable and connects it. The other kinds of connections you will find in both of these departments, there are multi-port transceivers and other kinds of things, connectors and that's one of these other people do. And basically, it's not at all uncommon to be in a situation where connected to the Ethernet is somehow some box. It's akin to a home and store LAN with lots and lots of connectors on it, all of which supposedly work, all of which are supposedly identical to a basic Ethernet transceiver function, which is generally some box with a connector on it. And to varying degrees, these things, in fact, are truly Ethernets. You may not be able to do TDR function and some other things with them. That's where they start to break down. For most of the purposes of Sniffer, this is perfectly acceptable. These other kind of connections are perfectly acceptable. It always helps to know what you're getting into. We were saying before, there are at least two situations I can think of where someone brought the Sniffer and found out that it simply couldn't be used. One case was an intercom switch, PBX, that emulates Ethernet. Basically, what they do is tell people they can put a workstation on their desk, have Ethernet at the back, they can plug and they can get this telephone switch, very, very large $120 switch, and it's Ethernet. You put the server somewhere and put the switch somewhere. Well, it's a simulation of Ethernet in that particular case. There is no Ethernet anywhere. There's no one place where you can watch the network, watch the packets, and see what's happening. The best you can do would be to get one of these multi-port type devices, and let's say you were in a customer that had one of these PBXs, which are Ethernet PBX, and they have these workstations which might be PCs or PCI in offices, and then here's an MV. Okay, you could put one of these multi-port devices in here and connect the Sniffer in, at least watch traffic to and from that particular device. But doing that and solving problems and then going to the workstation that's having a problem, and maybe there's another MV over here, and you want to load sharing, this is just doesn't lend itself to the type of environment the Sniffer expects. You just sit somewhere and sort of watch everything happen. You've got to walk around and watch everything there. The other case that you'll see are people who have broadband systems. And then broadband terminal connection, they say, oh yes, it's Ethernet. But again, it's not really Ethernet, it's 25 megabits, 10 megabits, etc. It's just really different, but there's a lot of loose terminology people call it Ethernet, and we're going to hear in a while talk about real differences even within truly low top. 2.3, where it's really bad enough. These things are really off the wall. With regard to these two different networks, putting aside the transceiver question, what we do is to use the transceiver type connection, which is DB 15-pin connector, as the standard interface. Okay. And then, basically, if you're going into a bar shop with a thick Ethernet type of system, very often they have a transceiver, it's already connected in. This makes connects along the workstation perhaps, and you just need a sniffer and a cable, and it works. And the only thing that's going to go wrong there is whether or not that transceiver really works, and issues like that. But on the whole, that's a very reasonable thing to expect when you plug onto one of those multi-port type of transceivers. That generally works. The other case is to go to a situation where they're using thin Ethernet. And we found that the best way to be able to handle both of those is to simply have a unit, have a cable, and also have a transceiver, known good transceiver that we'll talk about, that has a BNC style adapter. You can get that in nice little compact guys. I think the basic idea would be to have a sniffer, set of Velcro, with its cable, with its transceiver, and that's a kit. And you may only need the cable, you may need the cable and the transceiver, and then with this you can now connect into a Internet. As part of the recommended kit, I think you also need one short length of cable. That's a complete kit that pretty much will handle the two standard configurations. Again, it's all very simple when it works and when there are no problems. There are some things that one has to be careful of, which range from all kinds of surprises to fundamental issues like electrical safety. We can all, go with Ethernet and connect them. There's no reason why not to do that. But just walking up to a random piece of coax and unscrewing it could be touching to as well. And for that reason, the visual specifications and safety standards are quite careful about shielding cables and not allowing you to touch the ground and so on. The shielding part of the ground. Making sure that cable is grounded, but the same precautions apply to quote installing a sniffer as you would apply to installing a Velcro on PCI or something else, or no less. The other thing which is a potential concern is that in the world of computer networks and computers in general, the usual mathematical rules of transitivity and associativity don't work. A is compatible with B, B is compatible with C. Doesn't mean A is compatible with C. Logic does not prevail. So we know of many situations where there are systems that quote work. And you connect a sniffer, you connect some other box to it, and obviously it doesn't work. It's connected to the network, and it doesn't see, in some stations, it doesn't see all the traffic on the network. And the cause of that might be that on this network, one can have situations where this box can talk to this box. Okay. But it does so in a way that it's generating on the cable signals that are in fact less than standard, below the standard acceptable level. They're out of spec. But even though the transmitter is out of spec, fortunately the receiver is also out of spec. So they carefully compensate it, and this guy transmits a low level, but he's got a real hot receiver, so he hears it and everything's fine. And in situations like that, you start to run into all this weird stuff. You put the sniffer over here, and you see this station, but you don't see this station. You go over here, you see both, and you get out there, and you don't see either. Nothing adds up. Everything seems wrong. And the fact of the matter is, because you have lots of vendors and lots of different products, and they get built different days of the week, and they get chips from different sources. Not every single item is tested, and people don't look at analog levels. Suddenly, these weird, mysterious things happen. Again, I mention that only because they're not common. I mean, they're happening, they're down in the sub-percent kind of situations. Again, in a field situation when you're debugging, there can be serious diversions off the main path that people have to be aware of. When spooky things start happening, it's very often because these so-called standard systems aren't standard. And very often, if you go into a customer location, he says, "Oh yeah, just plug into this gateway here, just plug into this multi-port transceiver. Use this transceiver, it works." Again, it may not be exactly what you think. Being defensive is really important. Putting all that aside, And generally what you do is you just unpack it, plug it in, stick it on the network, and turn it on, you see everything. So that's really what happens. It doesn't take anything more than that. These are just a couple of kinds of mysteries that come up. I'm sure you're now on a long list of mysteries to deal with. So let's go through and take a look at how to actually use the product here. Turn off the lights on the post there on the side. Alright. This is a screen, an actual menu screen of the sniffer. I'm running on this new portable computer here. And what we're going to do is turn on, bring it up, see what it looks like. And we don't have a network here. Let me give something out to all of you. The two diskettes that you can use on some kind of PC equivalent. And basically, what that is are two different versions of a demo disk, one of which is the basic sniffer software with TCP IP protocols and some samples and examples from TCP IP data. The other one is a sniffer with the PCI interpreter, some version of the PCI decoder, and some examples of PCI data. And it also has on there a small tutorial. And what it is sort of a trial-size version. You can actually sit and run it, play with the menus, and do some things that we won't even get to today in terms of printing and whatnot. You can do that yourself. Now we don't have a network here, and with that demo disk, you won't have a network. So, what are you supposed to do? What was done is to provide a playback capability, so that rather than capturing data from a live network, you can use previously saved data as simulations of playback, and then actually tell it to use a file rather than a network as the source of data. And then you can turn on the filters, the triggers, okay, all the elements of the system can be used, except the data will be coming from file input instead of that. We'll use that now, so we'll be able to, in fact, change some options, play back the data, change some options, play back the data. Let's see what happens. Okay. The system is generally a menu-oriented system. The set of choices you have are shown in the center of the screen. So we can do things like test the cable, generate traffic, set various capture filters, trigger filters, save files, and a sort of a semi-logical progression in terms of the same flow that we saw of the system. is exhibited here. You may want to do cable testing or traffic generation in the front end of the product. And then you may want to do filters of the additional data, set a trigger, affect the capture that you're seeing, affect what it is you're displaying, save it to disk, and so on. Exit some of the flow of the system. But if you wanted, in this case, you turn on the unit and just press capture, which I'm not going to do right now because we're not connected to the network, and it would start collecting data and show you something. Its defaults being, look at everything, show everything, see everything, don't stop, and whatnot. So what we're going to do is some other things. But first, let's just explore the mechanics, of how we use the system. A few simple rules will help you out. So let's say we decided we'd like to test the cable. Okay? So we have a little quiz here, and have you help me press buttons. Okay, I'd like to move the cursor and go and test the cable. What key? Oh, now I start pushing up arrow. Okay, so press up arrow. Now press up arrow again. Press up arrow again. Now my cable testing, right? It's half what you expected. Well, the cursor didn't move. I tricked you. Text moved, cursor stayed the same. In general, the system, focus of attention will always be the center of the center panel. Okay? The text has to move, the cursor itself will always be here, and sometimes text will scroll off the screen. Like here, some of the options were, there was one more option, whatever, exit or something, is off the screen, there's a clue that's off the screen. And if I went the other way, the bottom, okay, it tells me that there are more options. Okay. By the way, the system really tries hard to give you some dynamic clues as to what's going on. You don't often have to pay attention to that, but if you've forgotten things, it helps you, or a real novice or someone who hasn't used it before, tells you things. Here it tells you only one or two lines of what that particular feature is. Okay, got. And down here gives you an idea of what you can do. So in this case, I can actually press enter to do cable testing. Okay, or I can use the arrow keys to go to some other option.
I need to help you right now. Would it just talk about things?
No. Let's go look at help. Here are some function keys that are labeled. Right now, this is saying that function key 10 is available, start capture. Function key 1 is available, which is help. Okay. These things will disappear and change. Notice that as they apply. But help itself, what it does is to provide really an online manual. Okay, it's a topic-oriented manual. These are the topics that we have, and there are some 30 topics, I don't know, 25 topics. And you pick a topic like the one that finds out about testing cable, go to that one, hit enter, and it brings up one or more pages of text about this. Okay? For context and for notes. Right, this is the one that the reference card high philosophy. Fairly expensive reference card that you can use. And in general, a couple things. Notice again, I'm using the cursor keys to move around up and down. In this case, in fact, the highlight is moving. And a few things I can always do. I'll hit the home key and always go to the top list. I'll hit the end key. Always go to the bottom of a list. Right. So if I press the letter, let me press the letter M. Okay. It goes to the next item from where you are with that letter. Okay. That will also always work. And the other thing you can always do is page up and page down. Page up and page down will always move you forward once one window's working or one page working. So the arrow keys will basically get you everywhere, and everything else just faster ways to go. Home and page up, page down, or just faster ways to do what you could do with the arrow keys. Thank you. I was wondering what to call it. How do you call that feature? know what. Class changing every day. I'm tuning in real time. One of the things we haven't done before was, for instance, right now the system's set up. There's a program that's running which is intercepting the large bit-to input that this overhead projector has and simulating keystrokes into this thing. It's here for doing things in the background. Do experiment and see if that works, for instance, and keep a version of the software. So bear with us. What happened to your network? Okay, so we were looking at that. So we see if I press the letter C, for example, it's going to go cable tester, capture filters, okay? Alright, now let's get down to files. Okay. And why don't you get a guess as to what's going on over here? Okay, notice as I change the options, stuff flashes by, and what are these verbs? Okay, they're the sub-options on the file. So I can load a file, save the file, stuff like that. Okay, so let's say I want to load a file. What key I can press, right arrow key. And the file submenu now is in the center of the screen. Okay, again, your current options are always in the center of the screen. You can always see the next set of options to the right. So if I go up and down, whatever options there are many here, you can come and go to the right. And this is where I came from. Okay, I came from the file menu. Okay, I'll load a data file, go over again with the right arrow key. Now here, this little icon basically generally means you can do something or change a value or something like that. In this case, you can select the file you want to load by hitting the Enter key. And the system reads the directory, figures out which files are legitimate sniffer files based on the names that they have, and then you can pick one, again, by pointing to it. And they're always automatically alphabetized and stuff like that. So we've done everything by pointing and hitting Enter. We haven't, in this case, typed anything. In case we have to type something, is if you want to save the file. You might have to do that. Alright. A little bit more on the mechanism of the system. Some other things that we're seeing here. Notice these little doohickeys. This looks a lot better, by the way, when it's not on a LCD screen. It's on a real CRT. But this is supposed to look like the following. You have a choice here of either displaying, when you're capturing, pairs of counts or individual counts for stations on the screen. Alright? Right now, this little arrow is pointing to pairs of counts. And the way you should think of this little thing is like a two-position switch. Right? The switch right now is pointing over here to pairs. We can turn it to this position. This is another two-position switch. This is a three-position switch. Okay? Where I can point it to either show frame counts, show kilobyte counts, or show network usage. The way we can change those things, so that's our current set of settings. We can see what our capture settings are by looking over here for some of the settings. And if I want to change it, I'll go over to the right. And let's say I wanted to use a linear bar scale. It says here, press the space bar to select this option. So I'll press the space bar, and the little pointer jumps, and that's showing me my current value. Okay. When I go up and change one of these options again, I point to the one that I want, put it in the center of the screen, put it over my feet, press space bar, and the arrow jumps in. I'm going to go for frame size. In that particular menu, we chose to put the settings more level to the right. In this case, then I have to go over there, and if I'd like to, for example, capture only 128 bytes of each frame, and I press the space bar for that option. I want to go back and hold it. That's from the beginning of the frame. The first 128 bytes, the first 68 bytes. Here's another type of option. When the system is collecting data, it has a some what we call the Geiger counter effect, which makes a clicky noise in the speaker, proportional to the rate at which data is. Most people fall into two categories: they either love it or they hate it. So in recognition of that, we designed a binary switch. You turn it on or turn it off, depending on which camp you come from. Some people consider it the best feature of the product. They can tell instantly from across the room what's going on in the system, and other people say, take that out of here, I never, come on. So this is the indication of a binary switch or on-off option. The way we ship it, it's on. If you don't like it, press space, boom, it's on. And you get a little X, which says basically that it's off. Okay? So there's a whole bunch of options that you'll see that are on-off options. And there are these other options, which are switches, elements. There's some other options where you choose a field. For example, here, I can specify where I'm capturing data from. The reason for having this over here is we can always tell where it came from. On the LCD screen, this doesn't show up very well, by the way. This is highlighted on the normal screen. So see what the option was that we're under capturing. And here, we can't capture from a network because we don't have one. So let's go and specify one of the files. And we'll just tell it to collect data from them. There are a number of fields, as I say, which have values, where the value is file name, or field name, or the name of the station we want to send traffic to. And in general, all those contexts have to hit enter in order to modify that field value. So, for instance, if I wanted to go to the traffic generator, let's say, I'll go over to the right, go up to the traffic generator. You see here, the traffic generator, I can send traffic to all stations with broadcast. I can send 1,000 byte packets, I can delay 10 bytes between packets. Let's say we wanted to send 500 byte packets. Okay, and we'll go over to the right, down, hit the enter key, and then it gives us a field. We can type in how big a packet we want to send. So 500 will tell us if it's not in its legal range. And that's the value. I believe it's true that almost all those types of contexts, we're changing the value if you decide you really do want to do it. You escape key and get you back to where you came from. Much like the file menu, whenever there's a choice of, for example, stations that you want to send something to, by hitting enter, what the system does is to give a list of the station addresses that it knows about, the names that it knows about. And you can pick one from that list. So if I want to send something to this sniffer, and I go to the end of the list, or type the letter T, hit enter, and it's going to send traffic to itself, which is actually a pretty good way to know if busy, not bothering anyone else. So that's the same effect, but keep it one. Loading high. For other cases where in a case like this, I might want to send data to a random number intentionally. I want to send traffic to station 1, 2, 3, 4, 5, which doesn't exist. In that case, I would pick this value called new station, hit enter, and then I usually type in the value I want. What's the name in this case? Now that's in my list of names. Alright. I think that's about all the mechanics. Okay? Move around pretty much the arcade. Select options by these check marks. Okay, so for example, we haven't seen this before, but let's try to figure out if we understand really what's going on here. This is capture filters, okay? This is specifying what it is I'm going to accept and what it is I'm going to throw the bit bucket off of my adapter. Okay? So who's going to tell me why he thinks this default setting needs? That's right, capture those good frames. So let's say I want to change the system because I think that I'm having a problem with lots of bad frames. I'd like to see how many bad frames am I getting. What should I do? Okay, so okay, I'm going to play a dummy. Who's going to call out a key? I'll press that key. Right arrow. Right arrow. next. Excuse me? One B. Okay. Space. Okay. Next. Go up. Down. Sideways. Down. Go up. Down. Okay, that would get very good. Up, G, right? Space. Okay, C. That's there. Okay. Collisions are short packets. I mean, they're well, it depends how many you're getting. If you're getting 100 per second, it's a certain rate of them is normal. Okay. A certain rate of collisions are reasonable. You never should have these things, although they may result in collisions. They cause things which are short packets. They may have just bad CRCs, depending what's happening. So I think of it as the opposite of good is bad. All these things are bizarre, non-normal, and if the rate of them is more than a certain level, whatever that is, we want to do it. So now if I started collecting data, all right, I would just see how fast that stuff is happening, and I can then actually look at that data when it came in. So maybe that's a bad cart that occasionally screws up its CRC. I can actually see the first part of the frame and actually see where that's coming from. All right, so that's what that part of the day was about. I'm going to change all this because we're actually more using capturing. We can do this later. We can do it downstairs on the real network. Okay, now what do we think these other, now we're on the capture filter section here, okay? So what do we think these other fields are? And those are other sub-choices within capture filters. You can just read what it says, we're not going to figure out. Here it says, set up a pre-filter for station addresses. So in our capture filters, we have station address class of filters. And over here, you can pretty much psych out what they're about by looking at the values that they currently have. Right now, we're set up to capture data from any station to any station. Okay. Also, this option is on, which says that we're going to capture data from any station to any station. And we'll capture both broadcast and non-broadcast data. Okay. What protocols are accepted on the network? Well, let's just look here. We're collecting the ISO network SAP, which is what PCI uses. There's another standard service access point that's defined called the SNAP. And then there's other. Again, something that you might want to do when you're looking at sort of, geez, anything weird happening are things like turn off things that are known, or in this case, it might be the only thing that should be happening is ISO. Turn that off. If you see anything coming in, what is it? Obviously, it's XDS, but XDS is other in this case. So if it were an XDS interpreter, then that would show up this line here, okay? And other would not include XDS. The word about writing a protocol interpreter, not now, in a few minutes, we'll give out some documentation on the Sniffer and manuals. And in there are examples of how to write a protocol interpreter. As I said, it can be done. And there's a fully worked example, which is all on 1 page long, that shows an interpreter for a service access point, protocol of which is made up example, but it's 1 byte field, that's the name of the device you want to talk to, and 1 byte opcode, and variable length, string, and that's about it. It takes C, Microsoft C, is used, and you basically compile this routine, and it's include the source, the object, the source is included with the system, you compile it, link it in, and then up here it would be, other, your SAP, whatever it's called. That would show up the window. And to do XDS, okay, for example, it could be something as simple as that. And the reason to do it as simply as that could be just to make sure that other is truly other. I mean, if in the normal DG environment, what you expect is ISO, or you expect XDS, even if you don't care what the XDS decode is, you can just say, hi, I'm XDS. That's good enough. Then other is really other. And by gosh and by golly, if there's other stuff floating around, you gotta find out where it's coming from. Maybe it's bad boards, maybe it's, we don't know what it would be, but that's how you might focus in on those kind of problems. Yes, we turn on some of these things. And then the next type of way that you can filter is based on a hex pattern. And here, again, you're looking at what the settings are. I can go over and pick a hex pattern, which is any 16-bit field, offset on any byte boundary in the record. And I can say whether or not I want to get packets that are equal to or not equal to that particular field. So again, if I know that certain return code is expected to be 0, and I want to find out only those packets for some reason that don't have the return code, I can use this to do that. Later, I'll show you how to find out what these values are, what these offsets are. But really, you don't even have a reference value. You have no developers available. You want to find out what the hell is a block failure. And in the field, we can figure that out using the information itself that it knows about, and then transcribing it. It is possible, those of you who wish to do it, it is possible to make this field actually be an arbitrary bit-oriented 16-bit field with no cares for any bit. I cannot actually type it in. If I go here now and do it, this version wants you to enter it in hex, so I can only type 1x34 or something. That would be my pattern. Okay. So I can't look at, the top 3 bits must be 111 and the rest can be don't care. I can't type it into the keyboard here. There is a way to do it. And that way has to do with what we call setups. And down here's my file menu. You may have noticed before that when I went to load a file, I actually had 2 different options for what I could load. We loaded a data file. It's data that has been captured. The other choice is to load a setup file. And what a setup file is all these little switches and collections and instrumentation, the front panel of the equipment. Okay, so you can spend a lot of time dealing with all this stuff and throwing all the little switches. And there are 2 reasons to use setups. Okay, one is you save it so that you can come back and do it later. Okay, at a later date, you have some standard way to do it. And the other case is you're so lost that the only way to figure out what's going on is to load a standard setup that resets everything back to the way it was. They can figure out what the hell's going on and sort of start moving around. Literally, you can set up so many different filters and options that all it tells you is, no events are seen. And sort of back out of the maze, you can load a default setup, which is one of the things we ship with the system. And you can save it as easily. Okay. So let's look at some data now. All right? Sure. Yes.
I wanted to put on a particular
right.
But I didn't know where I was going to
No. You have to know what offset it is.
But I think that all of this
That's right. You then have to write a program to do it, collect reasonable amounts of data, and look for it. Generally speaking, most of the fields and most of the protocols end up in a specific case, a particular customer, at a fixed offset. They may even vary from customer to customer depending on some details of implementation, but on the whole, it turns out that that generally works. But if you have something you're looking for, if you want to know what someone's electronic mail and you want to look for the word takeover, merger, okay, you would not be able to use it for that. Log on equals you probably would be able to find because that probably is at a fixed known offset. But the word merger it can take a little bit more work. Okay, one thing let me show. So here are our capture filters. Again, logically you set those are input filters. Right, then you have, based on that data flow, the trigger that you can set. The trigger is yet another pattern that you can set, different offsets in the frame. And down here is the criterion under which you stop capture. So let's take a quick look at that before we get ahead. And basically here, the way the system comes up is to be a continuous capturing or loop buffer. Stuff just runs off, all the stuff runs out of the buffer. Your options are to change this to stop when it's full, builds up, shuts itself down, or 5 different values of triggering where you'd like the trigger to be relative to the other data in the buffer. Okay, if you put the switch here, the trigger is the first thing in the buffer and all the data follows it. Put the option here, and all the data in the buffer is everything that happened prior to the trigger. The trigger is the last thing you see in the buffer. So you can figure out how something occurred and backwards. Okay, so let's capture some data. We said that we're going to capture data from the using this demo file. Now I'm just going to press F10 or I can hit enter. Enter. Now what's happening now is using that that file as a source of data. Change something to display out. And was building up a screen display while it replayed that data. Okay, that data up here was a counter which showed us how long it was playing the data. Okay, so this might be on the minutes, hours, whatever. 6 seconds worth of data here. Let me change some of the displays. Notice here the function keys. Now I can press F6, which are capture options. Press F6. And let me go back to the default way things work. Okay. So that's probably what you can see. Let's turn on here. Okay. Now here there's this moving bar graph. Okay, it goes back and forth. It shows the instantaneous rate. Tip of this thing is the instantaneous rate averaged over, I don't know, half a second or something like that. Of, in this case, frames per second. How many packets of frames per second are happening? And this gray area here is basically a high watermark. So if you have a network and it's normally running at 10 frames per second, but there's some big peak up here, you would see it bouncing back and forth, and then you can big peak on gray area. Okay. Anytime you can walk up to the thing and press F4, which is clear screen. See that? Essentially resets the counter, clears the screen. It still collects the data. I've just sort of erased my screen temporarily so I can see what's happening. Okay. Pause. Press pause. It's now not collecting data. What is collected, I've collected. And let's just take a look now at some of the other parts of the display. Essentially, it's always going to show us how much activity there is on the network, whether it's Ethernet or a Starlink type network. Down here, it's telling us the number of good frames, normal, healthy, upstanding, American frames are on that network. Then we have all these other oddball frames that it could count on the network. Right now, there've been 89 frames, and in fact, there were no collisions. This count of collisions or collision fragments, this count of CRC errors, alignment errors, and these will always show you what's going on in the network, regardless of whether you're accepting the data or not. It's separate. So basically, the sum of this number, this number, this number, this number is